Hi, I'm Holland Ladage, and I'm an undergraduate student at California State University, Northridge. And our research project's main focus is to model the rupture dynamics of strong ground acceleration that is greater than 1G in fault stepovers. And so in July of 2019, two really strong earthquakes struck the city of Ridgecrest and actually launched these pebble to boulder-sized rocks from their resting place along the lateral right strike slip fault trace. And so upon seeing these displaced rocks, we can actually infer that the ground acceleration has to exceed 1G, but these displaced rocks are really only concentrated in one area, and that is in the stepover region that's at the southern end of the magnitude 7.1 rupture. And similar observations were actually made along the right lateral strike slip fault of the 2010 magnitude 7.2 El Mayor earthquake as well. And so both of these earthquakes and displaced rocks demonstrate how a strike slip fault stepover can produce really strong and localized ground acceleration. And so what we want to do is answer two main questions of which geometrical stress conditions will produce ground acceleration that is greater than 1G in a stepover, and then what are the physical processes that will generate those accelerations. And so to model and illustrate ground acceleration in our fault stepovers, we're using the 3D finite element software called FaultMod, along with programs called Qubit and Trellis to create our fault meshes. And so within these fault meshes, we have a 5 Hertz resolution along the whole fault, and this allows us to see clear details within the models. So this dynamic modeling will help us determine how ruptures affect different stepover geometries, as well as simulate both the horizontal and vertical ground motion, as the rupture is propagating through the faults. And so that will help us gain a better understanding of how ground motion and rupture processes are related. And so our most important variable in this study is the fault geometry itself. And so we've separated that into actually 3 geometries. So we have aligned, separated, and overlapped. And so to do this, we create 2 planar faults. We've got one that's 30 kilometers long, and then we have one that's 10 kilometers long. And so what we do is we move this 10-kilometer fault so that it's either going to be separated from, overlapping, or in alignment with this 30-kilometer fault. And so we can actually separate it both horizontally and vertically up to distances of 5 kilometers. And so for this study, we are focused on compressional stepovers, since Ridgecrest and El Mayor are both compressional stepovers where we observed those launched rocks. And so we're also running these models for both subshear and super shear cases. And so let's get into some of our results. So we have run some models for all 3 geometries of stepovers. And when looking at the results of our project, we observed that the subshear cases produce stronger ground motion where we have stronger velocities and accelerations, which appear within our stepover region. And so these accelerations are created when the rupture hits the end of the first fault, and it's generated by that stopping phase when it hits the end of that fault. However, our super shear cases don't show any real effects in terms of the stepover geometry. Our highest accelerations really only occur at the super shear transition along the first fault. So when looking at the cone pattern we actually have pictured here for our super shear ruptures, we see that it produces motion that's actually directed diagonally away from our stepover instead of towards it. And so we also actually don't have any accelerations that exceed 1G for both our subshear and super shear cases for all of our models. And this is most likely due to the choices of our initial stresses. But we are looking to experiment with this in the future. So we are still in the process of running models, and we do eventually plan to run models for extensional stepovers, as well as look into which stresses and parameters will give us those accelerations that are greater than 1G. But come on over and take a look at our poster for more information, and let us know if you have any questions. Thank you.